Today, we're talking about key time parameters and functional safety. So we're going to review some of the different time parameters that people often ask about, sometimes get confused about, and we're going to do a quick review on how they're used in exSILentia to do the SIL verification calculations. But before we start, I should introduce myself. My name is Kate Hildenbrandt. I am product manager for exSILentia. What that means is that I'm responsible for the strategy, roadmap, and feature definition for the exSILentia software. I'm also focused on providing training and customer support for new and existing customers. So for that reason, I have my email address at the bottom here. If you have any questions for me, whether related to this webinar or not, please feel free to use that email address to ask me any questions you might have. So that's me. A little background on exida. We do have three main groups in exida. One is the product group. We do enterprise tools, which includes exSILentia, SIL Alarm, SIL Stat, etc. And these address obviously functional safety, alarm management, and cybersecurity. We also have lifecycle services. So we have consultants in-house who can help you, again, with functional safety, alarm management, and cybersecurity. And then we do certification and assessment of devices used across the industry, as well as personnel. So if you're familiar with our CFSC or CFSP programs, we do that as well. And hopefully all three of these can basically provide you with a safety solution overall. We do have offices around the world. I myself am located in our Pennsylvania office, which is a little outside of Philadelphia, but hopefully if you are listening from far away, you can see an exida expert that's located near you. We've also been doing projects internationally in our consulting group and certification group. So let's jump into the different time parameters that are used in functional safety and specifically play a big part in your SIL verification calculations. Obviously, the most obvious of these is the failure rate. The failure rate is defined as the number of failures per unit operating hours. It's represented by the lowercase Greek symbol lambda. And as an example, you might hear the failure rate of a device is 1 failure every 100 years. Some people might say it like that. Other people might use fits. You know, there are different ways to talk about the failure rates. So even though the failure rate changes with time, in functional safety, we approximate with a constant number based on an average over a period of time. And a little later on, I'm going to explain why we do that. But we have the equation for the failure rate. So lambda equals your delta number of failed units at the end of your time period over the number of successful units at the end of your time period multiplied by the time period. And so that is your failure rate calculation. So for many devices, again, the failure rate over time follows a trend, and that trend is called the bathtub curve. So over time, the trend shows the shape. You have a lot of failures that occur at the very beginning and the very end of the device's time in service. And then in the middle there, you can see it trends a little bit downward, but is relatively constant. So why is that? Let's talk about the bathtub curve. And how it impacts what we call the useful life of a device. So as you can see, the bathtub curve has a spike of failures at the beginning of the device's time in operation and at the very end. Why is that? Well, we have what we call infant mortality. This is weak units that are failing really early. So they're put into service, failing right away, and then are changed out with hopefully a more sound unit. At the end of the component's lifetime, you're going to have wear out. So here's a device that's been in service for a long time, whether it's constantly in use or whether it's simply just sitting there. There are many ways a device can wear out. And so that is why, obviously, there's a spike at the end of the device's life. In the middle, you have what we call the useful life of the device. So the failure rate is slowly declining, or it's completely steady for most of the time that the device is in service. In probabilistic analysis of safety systems, we simplify this by making the pessimistic approximation that is a constant failure rate. So again, just to back up this assumption that it's constant, we're assuming that the infant mortality failures are eliminated. Since weak units are identified usually before startup, you have your FATs, your SATs, you have a lot of testing before startup happens. And so we're assuming that that device never makes it into operation. It's eliminated, and so we're not going to skew the failure rate value in that direction. So we're assuming these are eliminated from operation. And so now, as you can see, we've taken that piece out of the bathtub curve. Let's talk a little bit more about this constant failure rate. We've talked about how it can trend down over time, but we're assuming pessimistically that it's going to essentially be constant as it is in the beginning. And so that is where the constant failure rate comes from for a period of time. It's an average until you get to wear out. So the failure rate during the wear out phase is pessimistically approximated by a useful life limit, meaning we're assuming that you're going to replace or refurbish that device before it hits wear out. And that's where that useful life value comes in. It is assuming an average after infant mortality and before you hit that wear out over that period of time. So the official definition is that useful life is defined as the area within the bathtub curve where the failure rate is relatively constant after infant mortality and before wear out starts. In functional safety, a constant failure rate is assumed, which is valid as long as the device is replaced prior to wear out. So that simplifies things, and that is why we assume that. Failure rates and useful life in exSILentia are actually provided by our failure rate database, which we call the SCRH, our Safety Equipment Reliability Handbook. As you can see, I have an example here of a generic pressure transmitter, and this is the data sheet that is embedded in exSILentia. We do allow for our users of exSILentia to see the entire data sheet. However, you don't need to be entering the numbers in yourself. When you choose the device, the failure rates are automatically applied. But it's nice to look at the data sheet for to see the basis of the data and to see things like the useful life. So in this case, the useful life for this generic pressure transmitter is 10 years. I can highlight where that is right here, 10 years. And so, and obviously you can see the different failure rates for the pressure transmitter. You have your fail high, fail low, fail detected, and fail dangerous undetected. And those are classified. Oh, and fail residual. Those are classified depending on how you use the device in your application. So if you're not using the SCRH, these numbers would be provided by the device manufacturer, and that's something that you can input directly into the tool or use however you're doing your design calculations. So for most devices, the useful life depends on the internal components and how those components wear out. So for instance, for an electrolytic capacitor, your useful life might be 10 years, but with a non-electrolytic capacitor, your useful life could be extended to 50 years. So a lot of it depends on the internal components of the device, how they're being used and how they wear out. However, it can depend on application-specific factors. So a valve could show no signs of wear out for 50 plus years in one application, but in a more severe application, it could have catastrophic failure in 6 months, perhaps due to a harmful chemical environment. So depending on the application, the useful life can also be impacted by that. So moving along, we're going to talk about the mean time to failure. This is defined as the average time until a device will fail, provided that it is operated within a specific operating conditions. The mean time to fail is valid only for the useful life. A quick example, mean time to fail of a device is 100 years. Basically, the mean time to fail is the inverse of the failure rate. So during the useful life, again, we're assuming a constant failure rate. So as long as we're within that useful life, the mean time to fail is the reciprocal value of the failure rate. Usually when we talk about mean time to fail, we're asked about some related parameters. So we want to define these up front. So the mean time between failures is always asked about, MTBF. And that is defined as the sum of mean time to fail and mean time to restore. The mean time to restore is defined as the sum of the mean time to detect a failure and the mean repair time. So as your system is running, whether you're doing diagnostics or you're doing proof tests, you will assume there is a certain time before you detect a failure. If you detect a failure in a device, you then have to procure a replacement, install it, and start back up. So that mean time to detect might be that proof test interval, and the mean time to restore depends on basically site parameters, how fast you're able to replace that. So then your mean time between failures is the time, the mean time to fail plus that mean time to restore. And obviously, these both depend on your operational philosophy and your testing strategy. Some of these can be accounted for within the calculation, some of these cannot. So those are the differences between those parameters, those related parameters. Moving on, let's talk about mission time. Mission time is defined as the time the devices in your SIF are operational, and the time between complete replacement or refurbishment of all devices in the SIF. So refurbishment should include replacement of all wear-out components, seals, valves, etc. Again, you can completely replace the device as well. Mission time has a significant impact on the PFD average calculation when imperfect proof testing is taken into account. So if you're doing your proof testing and you know the exact steps in your procedure, you know exactly what percentage of failures can be revealed during the proof test, which means that there are failures that may not be revealed. And those failures obviously could exist for the entirety of the SIF's life in the system. And so the mission time has that large impact on the PFD average. So you see this equation, PFD average, you're taking into account the proof test coverage, so that's the CPTI, times the dangerous undetected failure for the proof test interval, and then you're averaging that. And then you're taking 1 minus the proof test coverage, so these are the unrevealed failures times the dangerous undetected failure rate times the mission time over 2. So that's a simplified equation for a 1 out of 1 configuration. It can become more complicated in redundant configurations, but you get the idea of the impact of mission time on the PFD average. And to drive that point home, we have a few PFD charts. So in these PFD charts, and I'm going to do a spotlight, you see a red line, and this is the probability of failure on demand over time. You see some jagged edges every time this goes down. It's because a proof test is being performed. Even so, because proof tests are imperfect, you have a trend where the probability of failure on demand is moving up. Now that is averaged over the mission time. So this dotted line is showing the PFD average for this amount of time, which in this case, the mission time is 10 years, and the PFD average is 2.26 e to the minus 3. So if we extend the mission time, what impact would that have on the PFD average? If you extend the mission time to 15 years, the PFD average is 3.39 e to the negative 3, and that's because you're allowing that probability of failure trend to extend for a longer period of time. And over that time, obviously the average is going to increase. And then, of course, over 20 years, the PFD average increases to 4.61 e to the negative 3. And for the same reason, you're averaging over 20 years at this point. And so that is going to increase. So that is the impact of mission time on the probability of failure on demand average calculation. So let's basically summarize what we have learned with an example device. So let's consider a device with one failure every 100 years that is expected to begin wear out after 5 years, after which it should be replaced. It is used as a component in a SIF that will be operated for 20 years before all components are expected to be replaced. So now we have to identify for this device the following. What's the failure rate? What is the mean time to fail? What's the useful life? And what's the mission time? The failure rate is right up at the top. We're told that the device will fail once every 100 years. And so our failure rate is 0.01 failures per year. That makes the mean time to fail pretty easy as well. Our mean time to fail is 100 years because we know it's the inverse of the failure rate. The useful life and mission time might be a little bit more confusing. The useful life is the time before wear out. So if the device is expected to begin wear out after 5 years, the useful life is 5 years. And the mission time is 20 years because that is when the SIF will be that is how long the SIF will be operated before all components are expected to be replaced. So hopefully that gives you a good idea of the different time parameters for an example device. A lot of times we get the question, do these numbers even make sense? Why is mean time to fail greater than the useful life? So mean time to fail is an average time to failure during the useful life. Again, the mean time to fail is only valid during the useful life when we can assume that the failure rate is constant. So you can think of it a different way. In this case, on average, one device will fail every 100 operating years, which means if you have 100 of this device in service in your system, you can expect one failure each year. A mean time to fail of 100 years does not mean that the device will work for 100 years until failure. Again, it's only valid during the useful life. Another question we get is how can a device with a 5-year useful life be used in an application with a 20-year mission time? And this is because traditionally the mission time is operational parameter that applies to the entire SIF. So we assume the entire SIF has to be replaced or refurbished at the mission time. That way we're assuming that if the useful life for a specific device in the SIF is less than that mission time, that you will be doing routine maintenance to address that device specifically. However, exSILentia now allows users to specify mission time per group. And so let's look at what that looks like. When you define your SIF on a high level, you are defining a few parameters, including mission time for the entire SIF. So your as designed mission time might be, say, 15 years. And again, this depends on the operational philosophy. So you're inputting that parameter. However, we now allow you to go into the group, and in this case, we're defining some of the parameters for the sensor part. You can say, listen, this sensor has a useful life of 5 years, and I want to take that into account. I'm going to be replacing it, so I want the calculation to reflect that. So you can elect to do a group mission time by selecting the checkbox and enter in that 5-year mission time just for the sensor part. Now, what does that look like in our PFD chart? It definitely impacts the calculation. Basically, you can see how, and I'll highlight this again, your probability of failure on demand is increasing over time, and you can see the effect of the proof test bringing it down. But again, proof tests are imperfect. You can see then this large dip at 5 years, which is when we're assuming the device is being completely replaced or refurbished. And so it basically resets. And you can see how that would then bring the PFD average down. So for an overall SIF mission time of 20 years, the PFD average is still being determined over 20 years. However, for the sensor group, it's being replaced or refurbished after 5. So you can see how it's reset after each replacement. So in order to really take a look at how these parameters are used in exSILentia, I'm going to open the tool and show you how to model a SIF. So this is version 4 of exSILentia. Let me take my highlight off. Yep. And if you notice, the different modules of the tool that address the different tasks of the safety lifecycle are up top. I'm going to jump right to silver. And this is a completely blank project file. I'm going to add a new SIF. And for this SIF, you see we already have a sensor part, a logic solver part, and a final element part. However, there are a few SIF level parameters that I want to define right off the bat. So let's say this is a high pressure shutdown. And we can make that the description as well. And we'll give this a SIF tag and call it SIF 101. A lot of the information up front here is just reference. So I can select the analyst from the team members. I can put it in analysis state. I can put in any comments, and I can link any references. You might have in your project a PNID or something you might want to link to each specific SIF. From there on, you have to choose some parameters that are going to affect your calculation. So for architectural constraints, you want to choose which standard is your basis. Are you basing it on IEC 61511 or IEC 61508? You also have to choose whether you're going to consider a SIL capability in the tool. So if you're choosing a certified device, this is very easy. You simply choose that device or enter it in. You know the SIL capability. If you are not choosing a certified device, you can do your proven and use justification within the tool. However, if you prefer to document that outside of the tool, you can uncheck this box and consider SIL capability outside the tool. And then you can see the as designed mission time. Again, this is based on your personal operational philosophy or your company's operational philosophy. So this is an input into the tool. I'm going to leave it at 15 years. Then you have to choose, you have to enter the startup time. You want to indicate the demand mode. I'm going to leave it at low. And the tool actually keeps track of the different I/O channels, the inputs and outputs to the logic solver. And you can indicate whether you want, for this SIF, those I/O channels to be on separate modules or not. And that's going to slightly affect your calculation as well. So once you've input all of that information, you can start to model your SIF. So I'm going to start with the sensor. I'm going to add a sensor group. I'm going to say this is a pressure transmitter. So this is my PT101. In this case, the mean repair time is set at 24 hours. My proof testing strategy is defined here. Let's say I'm proof testing once a year. I'm going to choose devices from the SCRH, so I'm going to use the proof test coverage calculator, which takes the basically associated proof test, lets me know the coverage for that proof test for the devices that I've chosen here, and automatically gives me a proof test coverage. You can input the coverage yourself, however, because I know I'm choosing devices that are already embedded in the tool, I'm going to not put in a coverage myself. I know that this is a pressure measurement, so I set the measurement type to pressure. It's a high trip, we'll say, and if there's a fault in the transmitter, I want it to drive the signal over range. So I've set all of these parameters. I can start to choose my specific devices. First, I'm going to choose my process connection. I know exactly what I want, so I can come in here and filter. I can say this contains the device I want basically is clean service, and I can choose that from the SCRH. I can then add that device and it applies it. When I define my sensor, I'm going to go in again, and I know exactly what I want. In this case, I want my generic pressure transmitter from the SCRH, so I'm going to just type in this contains generic, and I'm going to choose my pressure transmitter and add that device. Now that I've chosen an analog device, there are a few extra options. You can see the PLC detection configuration appeared. In this case, I can indicate if I have out of range, if the PLC can detect out of range signals. I'm going to say yes. Do you have a transmitter fault filter? And are you tripping on transmitter fault? Also, we allow you to do external comparisons. So you can select this external comparison and indicate the coverage for that. I'm going to keep that off. So in this case, I'm leaving the mission time of the sensor at 15 years with the SIF. The one thing I have to do still is, because I've chosen my devices, I can hit the proof test coverage calculator and it will give me the proof test coverage for these two devices that I've chosen. Now that I've done all that, I can move on to the final element. I can add a group. I want this group to be 1 out of 2. So it's going to automatically set those final element legs. Because I've chosen to add redundancy, it's going to ask me, are these legs diverse or are they identical? If they're diverse, you have to obviously specify both of them. But because they're identical, the tool is allowing me to just specify them once. I can come in here to each leg and name them. So we'll have XV101, very generic, and XV102. Now here you can indicate the beta factor between the two legs. I'm going to leave it at 10%. We do have a beta estimator that allows you to go through some questions and determine if your beta factor should be lower than 10%. Again, you specify your mean repair time, your proof testing strategy, and in this case, you have a few different options for your final element. We do have other options, so this means anything that's not a remote actuated valve. So you can see here we have some generic relays, motor starters, speed drive interrupt, you have an electric horn, an alarm siren. So you can input any of these. However, I am going to assume this is a remote actuated valve. So I'm going to come in here and choose a solenoid. Again, I know exactly what I want, so I'm going to choose a generic three-way solenoid. And I'm going to choose an actuator valve combo. And generic is already set, so I'm going to select my device. In this case, I can hit the proof test coverage calculator because I've chosen my devices. I want to indicate some leg options. Is my valve open or close on trip? We're going to assume it's close on trip. If it's closed, is tight shutoff required? Or is the valve in severe service? So if the valve's in severe service, this basically means anything that the manufacturer isn't explicitly stating the valve is made for. So some applications might be rougher on the valve that might require a different set of failure rates for an accurate calculation. Another thing is, since I've chosen the devices, I can enable a partial valve stroke test. So I can enable that. I can set an interval, a duration, a coverage. I can indicate if it's initiated automatically. I can use equipment data for the coverage, and it gives me the PVST mode. I can also indicate which of the devices the PVST will be performed on, if in fact it is not performed on all devices. So we don't want to assume that. I'm going to not apply PVST, just so that we have a pretty simple example here. Now that my final element group is modeled, I can come in here and choose my logic solver. And again, I'm going to go with a generic, so I can filter through and choose a generic SIL certified PLC and apply that. Again, because this is from the database, I can apply the proof test coverage using the proof test coverage calculator. Now you can see that my SIF automatically calculated the results, and I'm achieving SIL 1 with a risk reduction factor of 55. Some of the results include the risk reduction factor is shown for each part of the SIF, so the sensor part, the logic solver part, and the final element part, and then finally for the total SIF. The same is shown for the PFD average, the mean time to fail spurious. Your SIL according to PFD average is shown here, as well as your SIL according to architectural constraints. I have the SIL according to systematic capability shut off, so it's basically saying not applicable. And the reason I did that is because most of my devices are generic, so I don't have the SIL capability in the database for that. If I click this again and click calculate, it's going to tell me that my SIL capability is 0, except for the SIL 3 certified logic solver. So now my achieved SIL is 0, which is appropriate if I haven't done proven and use justification for my generic devices. So let's assume that I've documented that outside of the tool. You can see my response time, and then we have PFD average and MTTFS contribution pie charts. And basically what this is saying is if I have not achieved my target SIL level or my target risk reduction factor, this is letting me know which part of the SIF I should focus on to basically change my modeling, maybe adding redundancy, perhaps changing the proof test strategy for, in this case, the final element, because that is contributing most to my PFD average. Same goes for MTTFS. If you want to minimize that, you can use this pie chart to determine what part of the SIF to focus on. And then finally, you can take a look at the PFD chart. So in this case, you're seeing the PFD average for the entire SIF. So that's, again, here, let me highlight it. That's again, that dotted line is showing the PFD average. The red line is the probability of failure on demand over time. And you can see each year I'm doing a proof test. So the impact of the proof tests are shown in the chart as well. We also show this for each part of the SIF. So you can see the chart for the sensor group specifically, for the logic solver group, and for the final element group. Now, if in this case I have a mission time of 15 years, but I know that my sensor has a useful life of 5 years, I can come in here and set a mission time for my sensor group. And it's pretty easy to do. You just click group mission time and specify your mission time for that specific. Let's say for the final element, we can get fancy and say this is going to wear out after 10 years. So I'm going to specify a mission time per group there too. At this point, I'm calculating, and we'll see how that affects the PFD charts. So in this case, you see the PFD for the entire SIF. You can see that, again, you see the impact of the proof test, but also the impact of those specific mission times. This is easier to look at for the specific groups. So I had set the mission time for the sensor group to 5 years. So you can see how it's resetting every 5 years. The same goes for the final element group. This is resetting after 10 years because that is the group-specific mission time. If the logic solver remains the same because its mission time is 15 years. So you can see the impact that that has on the SIF. So there is a pretty quick overview of how you might model a SIF in exSILentia and how the different time parameters affect that calculation. I do have some questions here. One is, where do you specify the SIL target in the tool? And this is a good question because here you see my requirements are blank. Again, I have just simply opened a blank file and started. If I'm using only silver, I can come into the view for my SIF and I can put my SIL target here. So let's say that my required RRF is 55 and my required SIL is 1. And now you can see the requirement up top. This can also be done by going through your analysis in exSILentia. So as you can see here, we do have PHA module, we have a LOPA module, SIL selection, and SRS module. In many cases, if you're using those, you will already have a required SIL and a required risk reduction factor that data is transferring over from your analysis. However, if you're just using silver, you can do what I just did and enter it there. Another question I'm getting is, what if a device is not replaced? So essentially, and I think, yep, I'm assuming this refers to the mission time. Again, the mission time is the time that your SIF is in operation until it's completely replaced or refurbished. If it's not replaced, we're hoping it's properly refurbished. If you're not doing either, then essentially your SIL verification calculations are not valid. If I have modeled this SIF assuming these specific mission times and I don't do the due maintenance to replace or refurbish my devices, then I'm basically at risk of a hazard scenario where my SIF is not responding and mitigating that hazard. So my achieved SIL and my achieved RF are dependent on these parameters. And once I stray from these parameters, it is no longer a valid achieved SIL or achieved RF. Okay. All right. So if I go back to my slides, that should have been a good overview of the different time parameters in used in our functional safety design calculations, and hopefully some good information on how to model a SIF and exSILentia and how those time parameters affect that calculation. If you want to know more, you can find us on social media. exida is on Twitter, on Facebook, and on LinkedIn. If you have a suggestion for a webinar topic, we really like these webinars to be useful, so please send your suggestions to academy@exida.com. We also have some courses coming up this spring, so you can see the various courses here. We do have an online course going on right now for cybersecurity software development. Coming up, we have layer of protection analysis with exSILentia, March 12th, and then March 13th and 14th, it's SIL verification with exSILentia. So that's teaching you how to do these things with the tool. We have fire and gas detection, design and technology in Houston that same week. And you can see we have a lot going on this spring in March and April. These are the North American courses. We do have courses all over, and you can find the full training schedule at exida.com/training. So let us know if you have any questions on the training. If I missed anybody's questions, I can basically email you directly. I do like everybody to benefit from the questions, so if there are a lot of them, I will prepare basically a question and answer document to send out along with the slides and the recording. All right, so thank you so much for tuning in, for listening, and take care.